in the first lecture we looked at complex variables and we looked at functions of a complex variables. Now, I intuitively invoked the idea of continuity of functions when I was talking about branch cuts. Now, let us make it a little bit more formal, okay, the idea of continuity. Now, there is some formal definition of limits, okay, which you might be familiar, okay, how to take limits of functions and how to define continuity of functions of real variables. Okay. I will not be describing that in too much detail, but I will be using some of those ideas. So, what I want to do is talk about complex functions, and there are interesting ideas about continuity, differentiability and so on. Okay. So, let us start with let us start. So, suppose you have a complex function f of x y, okay, equal to u of x y plus I v of x y. Okay. So, this is continuous if u of x y and v of x y are continuous. Similarly, you can say it is differentiable if u of x y and v of x y are differentiable. Okay. So, continuous, and let me write in bracket differentiable. Okay. Okay. Now, if a function is continuous, so if f of x is continuous at x equal to x 0, okay, then limit as x tends to x 0 f of x equal to f of x 0. So, this is a definition of a function being continuous at that point. Okay. And formally you can say that you can also say that this is same as limit as x tends to x 0 from the positive direction, and this should be equal to limit as x tends to x 0 from the negative direction. Okay. And all of them should be equal to the value of the function at x 0. Okay. So, now in complex plane, what we want to say is that limit of f of z as z tends to z 0 equal to f of z 0. Okay. Now, formally this limiting procedure. So, here when we say x tending to x 0, we write it as x tending to x 0 plus or x tending to x 0 minus, okay. Or you say that x minus x 0 or absolute value of x minus x 0 less than delta, some small number. Okay. So, we say that what we will say is that if absolute value of x this is the formal definition of this limiting procedure. Okay. So, what you will say is that for every I mean this can be found for all f of x minus f of x 0 less than epsilon. Okay. So, what it means is that you can choose an arbitrary small epsilon, and you can always find a delta neighborhood such that within this neighborhood this function is arbitrarily close to f of x 0. Okay. So, this is a formal definition of the limit. Now here what is done in complex variables is you say absolute value of z minus z 0 less than delta. Okay. Now, this is absolute value in terms of the complex absolute value, okay, and you say absolute value of f of z minus f of z 0 less than epsilon. Okay. So given an arbitrary epsilon, okay, you can always find a delta such that when z is in the neighborhood of z0. So we say z is in neighborhood of z0. Okay. So in the complex, when you are dealing with continuity in the complex plane, okay, so if I have a point z0, okay, the neighborhood is actually this whole region. So this z minus z0 equal to, so this is the neighborhood z minus z0 less than delta. So this neighborhood looks like this region of size delta. Okay. So that is what this neighborhood looks like. Okay. So continuity in complex plane always involves a neighborhood. So it should tend to, the function should be continuous whichever direction you go. So now if you want to check whether f of x y is continuous, you just have to see whether u of x y and v of x y are continuous. If they are continuous, then f of x y will be continuous, and similarly if u of x y and v of x y are differentiable, then f of x y will be differentiable. Okay. Now another interesting result, okay, regarding differentiability. Okay, and this has to do with the way this neighborhood is taken. Okay. So when you take derivative, okay, when you take derivative f prime of z, okay, this is actually df of z by dz. Okay. So how do you take this dz? Okay. Now formally, if you write f prime of x equal to df by dx, okay, then you write this as limit as h tends to 0 f of x plus h minus f of x divided by h. This is how you define the derivative. Okay. Now in this case, can you have an equivalent definition in this case? So let us just follow the usual way. We will say limit as z minus well. So let me do it slightly differently. So this is the derivative at x. So f prime at x 0 is equal to df by dx evaluated at x equal to x 0. I am just writing it very formally. So this is limit as x minus x 0 tends to 0 f of x minus f of x 0 divided by x minus x 0. Okay. So this is how you define the derivative. Okay. Now I'll use the same way. So f prime at z 0 is equal to df by dz evaluated at z equal to z 0. This I'll write as limit as z minus z 0 tends to 0 f of z minus f of z 0 divided by z minus z 0. Okay. So this is the definition of the derivative, just exactly the way you define the derivative in this case. Okay. Now there is a little subtlety in this. Okay. Now if the derivative is defined, then it should be the same whichever direction you go. Okay. So if I have a point z 0 in the complex plane, okay, then as I said z minus z 0, okay, z minus z 0 less than delta. So this is my delta neighborhood. Okay. Now when I say z tends to z 0, I can have a point anywhere here. It can go this way, it can go this way, it can go in this direction. So, I can take a point anywhere inside this neighborhood. So, and I move it towards this, okay, and all of them should give the same value. So, the derivative, whichever direction I go, I should get the same derivative. Okay. Now, you can take two simple cases. Okay. So, let us take two cases. We will take the going along x direction. Okay. So, that means what I am doing is I am going to z0 only along x direction. I am not changing the y part at all. Okay. Then what I will have is, now if I write f prime at z0 is equal to limit as x minus x0 tends to 0. Now, f of z, I can write it as I can write this as u of x y plus I v of x I times v of x y minus u of x 0 y 0 plus I v of x 0 y 0 divided by, now what I have is, instead of z minus z 0, see z minus z 0 formally should have x minus x 0 plus I y minus y 0. Okay. So, that is what it should have, but in this case we took this going to 0. Okay. So, now what I have is just now again y is equal to y 0. So, what I will write this, I will simplify this in the following way. So, 0 u of x y 0 minus u of x 0 y 0 divided by x minus x 0 plus I v of x y 0 minus v of x 0 y 0 divided by x minus x 0. So, what I will write this? I will write this as now this is just like a derivative with respect to x. So, I can write this as u x u underscore x, that is du by dx. Okay. So, I will write it as du by, or actually in this case it is partial of u with respect to partial of x evaluated at x 0 y 0 plus I partial of v with respect to partial of x evaluated at x 0 y 0. Okay. And we will use the short notation, you will write it as u x plus I v x, okay, where u x is equal to dou u by dou x evaluated at x 0 y 0. Okay. So, this is along the x direction, I can write this way. Now, suppose I just vary along the y direction. So, along y direction, okay. Now, what I have is f prime of z 0 is equal to limit as y minus y 0 tends to 0. Okay. Now, along the y direction, what I have is so I have u of x 0 y, okay, minus u of x 0 y 0 divided by, now you look here, there is a factor of I here. Okay. So, there is I times y minus y 0. So, along what you have is x is equal to x 0, but this is not equal to 0. So, you have the first term going to 0, okay, and you should have plus I times, now you have v of x 0 y minus v of x 0 y 0 divided by I times y minus y 0. Okay. Now, what you see is that this is equal to, so 1 over I is minus I. So, I will write this as minus I dou u by dou y evaluated at x 0 y 0, and you have, in this case the i's will cancel. So, you have plus dou v by dou y evaluated at x 0 y 0. Okay. So, what I can write this as? I can write this as minus I u y plus v y, okay, where u y equal to dou u by dou y evaluated at x 0 y 0, and similarly for v y. Okay. Now, now notice that the same derivative has these two different forms. Okay. Now this form and this form should be the same. Okay. So, since they should be the same, they can only be the same if the real parts are the same and the imaginary parts are the same. So, this implies u x equal to v y and v x equal to minus u y. Okay. So, these are conditions that are necessary in order for the derivative to be defined. So, if you want to have a derivative of f of z, so these are necessary conditions for f prime of z to be defined at any point z 0. Okay. These conditions are called the Cauchy Riemann equations. Okay. And it is a very powerful theorem, because what it says is that if you just have a function, if you just have f of x y equal to u of x y plus I v of x y, okay, then in order for f of x y, in order for f of z to be differentiable at any point, okay, it must satisfy u x equal to v y and v x equal to minus u y. Okay. So, and what and by doing this exercise, you realize that you realize something very interesting, that derivatives, not all functions, if you just write some arbitrary function, then it is not going to be differentiable. Okay. So, differentiability in a complex plane is actually quite a strong statement. Okay. And let me emphasize this, that I will just say that differentiability in complex plane is a strong statement, okay, relatively strong statement. Okay. That means, if I just write functions, if I just choose some arbitrary u and arbitrary v, then most likely it will not be differentiable. Only those functions that satisfy that the derivative x derivative of u should be equal to the y derivative of v, and the x derivative of v should be negative the y derivative of u, only those functions will be differentiable. Okay. So, this again this illustrates that how very simple ideas, very simple ideas of functions, they become more complicated, and in fact in fact this will turn out to be a huge simplifying factor when you are doing integrations of complex functions. Okay. So, I will conclude this lecture for now. Okay. In the next lecture we will look at other properties of complex functions. We will look at integration of complex functions. We will look at something called the residue theorem. Thank you.